Hi, I'm Robin. I will present to you some experimental work I have done together with Jakob Stærk Østergaard and Vincent F. Hendricks at the Center for Information and Bubble Studies at the University of Copenhagen on the wisdom and persuadability of people in online discussion threads. We were interested in this question because there is currently a debate in the collective intelligence literature, and especially in the wisdom of crowds literature, pertaining to the role played by social information. Is social information, for instance, like advice given by others or just by observing what others have done, is such information helpful, or does it do more harm than good? So, we started off with some initial testing on Facebook. Following the lead by Francis Galton, we took a nice picture of a very stout ox and asked friends to estimate its weight. They did remarkably well. This was puzzling in a way, because people were influenced by each other. They could see all the estimates made so far. Now, if you read the classical crowd aggregation literature, you will find the claim that crowds only become wiser when people make their estimates independently from each other. The reason being that any individual bias and confusion tends to average out, so that the mean and median estimate tend to become very accurate. On the other hand, if people can see each other's guesses, judgment errors may correlate with each other, which in turn will undermine crowd accuracy. So we set up a much more rigorous experiment in which we asked people to estimate the number of dots on a screen. So here you can see a screenshot of a typical experiment we did on a Mechanical Turk, where a participant in a thread has to guess the number of dots in the image, while also observing some of the estimates made by preceding estimates. In this case, the 9 previous estimates made by other participants in the thread. We collected a total of nearly 12,000 estimates from Amazon Mechanical Turk. About 6,000 of those estimates were collected from participants who were placed in 12 different threads, where they successively estimated the number of dots in 4 different images with either 55, 148, 403 or 1,097 dots respectively, while seeing either V preceding estimates with V being 1, 3 or 9. So these are the historical threads, we call them. Another 4,000 estimates were collected from participants placed in 12 new threads who were shown the same images while seeing the V highest estimates made so far. So these we call the manipulated threads. Finally, the last 2,000 estimates were collected from participants who were shown the same images again, but with V equals 0, corresponding to a control condition for each image and no social information. We interpret the number of dots D as the task difficulty, while the number of visible previous estimates V is interpreted as the degree of social information. Participants were placed randomly in one of the 28 threads and made their estimates one after another. So no participant who had seen a certain image would be able to participate in another thread containing the same image again. In addition to a participation fee and a variable weighting fee, all participants in a thread received a bonus of $1 if their estimate was within 10% of the true value. For the statistical analysis of the results, we compared the log ratio of thread medians, M, using a linear normal model in order to quantify the difference between threads in terms of their difficulty, given by log D, and social information, given by the categorical variable V. So look at the top graph here. On the y-axis, we have the median log ratio, which gives a symmetric measure of the collective estimation error. And on the x-axis, we have the logarithm of the task difficulty D. For the least difficult tasks with D55 and D43, participants do well, no matter how much or how little social information they have, which you can see by the colored categorical variable V. For higher difficulties, however, social information makes a difference. While the control group in red shows an increasing underestimation bias for higher D, the thread in which people can see 9 preceding estimates performs significantly better and is able to counter the negative effects of task difficulty. In fact, the median estimate of all historical threads with V equal 9 is wise in the sense of being statistically indistinguishable from the true value shown by the dotted line. So, we can conclude that collective performance of historical threads declines significantly with increasing task difficulty, which is higher D, but it improves significantly with increasing social information. This supports the claim that crowds indeed may become wise under pristine social influence. The manipulated threads, however, in the lower graph, show a large positive bias for 3 and 9 views, which increases with D, implying that when a task becomes more demanding, the amount of filtered social information has a highly detrimental impact on thread performance. People simply start to guess really high numbers when they see high numbers. While our analysis of aggregate results clearly demonstrate the counteracting forces of task difficulty and social information, even more interesting results can be found when we look at the heterogeneity of individual guesses and compare them to the type of social information they are based on. Now, a good way to tease out these interactions is to use probabilistic Gaussian mixture models, GMMs as they are called, since they have 2 properties that are highly valuable in the context of crowd aggregation research. First, GMMs are comprised of several Gaussians which fit well to the highly right-skewed and long-tailed distributions emerging from free response elicitations. Second, GMMs associate a measure to each data point describing the influence of social information on that particular participant. This measure aids us in associating participants with subpopulations in the data related to how people act under available social information without using any prior knowledge of these subpopulations. So this model gives a persuadability score, which we call beta, which is high when people are highly influenced by the social information they can see, and small when people are not influenced or when they are skeptical about the information. So let's see how this works for a particular thread. Here are the results for a pristine thread in which people see an image with 1097 dots and only 1 preceding estimate. The top plot shows the log ratio of estimates over time, with the geometric mean of the social information shown by a dotted line. As the log ratio is a symmetric measure of estimation error, you see a somewhat random pattern of estimates around the true value, given by the horizontal line at 0, although, as we saw before, there is a systematic underestimation bias for large D and small v. As you can see, each estimate has an associated color, given by beta, which is the effect of the social information on each participant, calculated as the weighted average of the individual states of the GMM. A high value above 0.6 is shown in blue colors, implying a large effect. A low value around 0 is shown in red, implying little or no effect. A medium value around 0.2 until 0.5 is shown in brown and green colors, suggesting a compromise between the 2 extremes. The bottom left plot shows the log ratio of the estimates as a function of the log ratio of the social information, indicating how different people use their social information. The more they align with the identity line, the more they tend to follow their social information. The bottom right plot shows the cumulative distribution of the individual persuadability scores beta with a 95% confidence interval derived from the fitted model. It clearly shows that how people can be categorized into those sleeping dogs or unpersuadables in red that do not take other people's estimates into account. The persuadables that tend to follow others and a large group of green compromisers in between who try to strike a balance between what they see others have guessed and what they believe themselves. Of course, such categories are only proximate. Given a participant has a personal estimate much in line with the social information seen, this participant may be categorized as a persuadable or as a compromiser, when in fact this is only partially true. In general, however, the distributions are remarkably stable across threads, which suggests that people indeed may be categorized by these overlapping categories. What becomes abundantly clear when examining the results is a sharp contrast between how people act in pristine historical threads where they can see the preceding estimates and how people act in manipulated threads where they see only a filtered selection of previous estimates, namely the highest ones made so far. Here is an example of a manipulated thread where participants see an image with only 55 dots and the highest previous estimate made so far. People are not really influenced by this single high value, probably because it's easy to see that the actual number of dots in the image is much lower. But as soon as the number of visible estimates increases from 1 to 3, more people tend to follow, or at least compromise, as you can see from the green colors in this picture here. This shows that there may be a weak bandwagoning effect at work here, making it more likely for people to follow others the more people have done so already. If we also increase the difficulty of the task from 55 to 148 dots, the numbers of manipulated people increases as well as the degree of their manipulation, as you can see by the emergence of the blue colors here in the plot. This general pattern continues, and in a thread with 1097 dots and the 9 highest views, we see huge errors in most estimates. It shows that at least 30% of participants in this thread are strongly influenced by the filtered information given to them. So, to conclude, does social information help crowd wisdom or does it not help? The answer is yes. Social information in online estimation threads does help when people have hard problems to solve and when the information available to them is pristine, and when it's representative and honestly made. However, if the social information is filtered and not representative of the thread population, it becomes manipulative and may fool a substantial proportion of people, which of course interferes with any aspiration to harness the powers of collective intelligence. Moving from the aggregate to the individual level, we find that people can be assigned a persuadability score by using Gaussian mixture models. Persuadability generally increases with task difficulty and with the amount of social information provided to them. But in the case of strong manipulations, we may see a split between a minority of persuadables and a majority of skeptics. We do not know how much these influencing effects are transferable to other domains. However, due to the general nature of dot estimation, we suspect the effect to be substantial in other settings as well, and also for other questions, especially for those that are more emotional, subjective, and political in nature. In computational social science and decision-making research, there's an acute need to further investigate the types of disturbances in online threads and crowds, such as filters, rankings, likes, and recommendations, as well as the types of reactions to those disturbances. To the end of designing future collective intelligence systems, we need to be vigilant about the way social information is gathered and framed. Crowd knowledge and thread wisdom is very fragile and can only be maintained and nurtured with strong controls upon the way it is cultivated and recovered. Thank you very much.